Is there any relationship between end-tidal carbon dioxide and cardiac output? Would changes in EtCO2 reflect changes in cardiac output? Welcome to this episode of Doodly. During the course of this episode, we will try to understand the relationship between ventilation, pulmonary blood flow, and how changes in ventilation and pulmonary blood flow would affect EtCO2. Thereby, try to understand whether EtCO2 can be used as a surrogate marker for cardiac output. Let us take the case of an average sized adult who's producing about 200 mils of carbon dioxide every minute, which needs to be exhaled out. For the ease of calculation, I've considered EtCO2 to be about 40 millimeters of mercury. I have made two further assumptions. The first is there's no difference between the alveolar or arterial partial pressure of carbon dioxide and end-tidal carbon dioxide, even though EtCO2 is about 4 to 5 millimeters less than the alveolar or arterial CO2. The second is the minute ventilation and alveolar ventilation are the same, even though alveolar ventilation is less than minute ventilation. Now, in order to eliminate 200 ml of CO2 in a minute with the EtCO2 of about 40, we would need a ventilation of around 4 liters. And in order to keep a ventilation perfusion ratio of 1, the pulmonary blood flow would have to be a matching 4 liters. This minute ventilation of 4 liters is not an arbitrary number. I will try to explain over the next few slides as to how we arrived at this number. In order to understand that, we need to understand two additional concepts. The first of one is the oxygen cascade, and the second one is the Dalton's law of partial pressure. Oxygen cascade, as shown in the diagram, represents how oxygen flows from atmosphere to the mitochondria, and in the process, how the partial pressure drops at various stages. The first one happens due to humidification at the upper airway or the conducting airways. The second one happens at the level of alveolus due to addition of carbon dioxide. The third and fourth ones are mainly due to ventilation perfusion mismatch and shunt. However, for the purpose of this discussion, we will confine ourselves only to the first two stages of the oxygen cascade. The next thing we need to understand is the Dalton's law of partial pressure, which states that in a mixture of gases, if a gas contributes a certain proportion of volume, it would contribute a similar proportion of the total pressure as well. For example, if oxygen contributes or constitutes 21% of the atmosphere by volume, it would also contribute to 21% of the total atmospheric pressure. The atmospheric pressure at sea level is about 760 millimeters of mercury. Now, because nitrogen constitutes about 79% and oxygen 21%, they also contribute a similar proportion to the total pressure, thereby contributing about 600 and 160 millimeters of mercury, respectively. Now, the first step of the oxygen cascade is because of humidification of the inspired air happening in the conducting areas. The inspired air is fully saturated with vapor with at body temperature of 37 degrees. The saturated vapor pressure is about 44 millimeters of mercury. Now, with the addition of vapor, we have three gases contributing to the volume as well as the total pressure. So, in order to arrive at the new pressures for oxygen and nitrogen, we deduct 44 millimeters of mercury from 760. That gives us a value of 716 millimeters of mercury. Nitrogen and oxygen contribute 79 and 21% of this respectively. which translates to 566 millimeters of mercury and 150 millimeters of mercury, respectively. The second step of the oxygen cascade is the drop in partial pressures due to addition of carbon dioxide at the level of alveolus. So presume the EtCO2 or the alveolar carbon dioxide to be about 40 millimeters of mercury. Now we have a fourth gas. In order to find out the respective contributions, we deduct 40 millimeters from 716, which gives us a new value of 676. The oxygen and nitrogen contribute 21 and 79% of this value, which translates to respectively 142 and 534 millimeters of mercury. Uh, if we now look at the composition of the alveolar gases, there are four components: nitrogen, oxygen, carbon dioxide, and water vapor. Carbon dioxide being about 40 millimeters of mercury, uh, as a percentage of 760 millimeters, it would roughly translate to 5.2%. I have rounded it up to 5%. So, thus, 40 millimeters of CO2 would translate to 5% CO2 as a composition of the alveolar gas. In order to eliminate 200 mils of carbon dioxide in a minute as a 5% mixture, we would thus need 4 liters of minute ventilation. That's how we arrived at the minute ventilation of 4 liters. Thus, as we saw in the previous slides, in order to eliminate 200 mils of CO2 in a minute as a 5% composition of the exhaled gas, we would need 4 liters of minute ventilation. In order to keep the perfusion ventilation ratio at 1, a matching 4-liter pulmonary blood flow has been assumed. Now, if we have understood this concept, we move on to the next few slides wherein we see the effect of altering ventilation as well as pulmonary blood flow and the effect it has on CO2. Now, in the scenario depicted in the next slide, we keep the perfusion constant at 4 liters. However, we see what happens if we double the ventilation to about 8 liters instead of 4 liters. Now, as we still need to eliminate only 200 mils of CO2 in that minute, 200 mils as a proportion of 8 liters would become about 2.5%. So, as a result of which, EtCO2 also drops to about 20 millimeters of mercury, which is about half of what it was with a minute ventilation of 4 liters. Now, in the next scenario, we keep the perfusion at 4 liters, but half the minute ventilation from 4 liters to 2 liters. Now, we still need to eliminate 200 mils of CO2 in the minute. So, that 200 mils of CO2 eliminated as a part of 2 liters would translate to about 10% by volume, as a result of which EtCO2 also would contribute roughly about 10% or 760 millimeters. I've rounded it off to about 80 millimeters of mercury. Now, in the third scenario here, we are going to keep the ventilation constant at 4 liters, but reduce the pulmonary blood flow to about 3 liters. Now, because of the higher diffusing nature of the carbon dioxide, whatever carbon dioxide comes to the lung from the pulmonary blood flow diffuses into the alveolus. So the blood flow would be the limiting factor into the lung, which would determine how CO2 is eliminated. So presuming that 4 liters flow was bringing in about 200 ml of CO2, each liter roughly brings about 50 ml of CO2. But now because the flow is only about 3 liters, we expect about only 150 ml of CO2 to come. This 150 ml of CO2 is eliminated in 4 liters of ventilation. That translates to about 3.75% by volume and a similar proportion uh, of the pressure as well, as a result of which the partial pressure of EtCO2 comes down. The new value of EtCO2 would be around about 28 millimeters of mercury. As we saw in the previous slides, both ventilation and perfusion can alter the EtCO2 levels. So, in any scenario, if we keep the ventilation constant, uh, the pulmonary blood flow would become the predominant or the only determinant which would determine what happens to the EtCO2. Thus, if the pulmonary blood flow is reduced, EtCO2 would come down. Contrarily, if the pulmonary blood flow increases, that would translate to an increase in EtCO2. Now, because pulmonary and systemic circulations are in series with each other, whatever blood comes to the lung from the vena cava has to go to the left side of the heart, and the left side of the heart has to pump it out into systemic circulation. Thus, the pulmonary and systemic blood flow would be similar, even though we cannot or not measuring systemic flow, but because by keeping minute ventilation constant, the changes in EtCO2 would linearly reflect the changes in pulmonary blood flow. We can use EtCO2 as a surrogate marker for a trend in changes of the left sided output or the cardiac output. I hope this was helpful. Understanding this relationship between EtCO2 and cardiac output helps us approach a patient in hypotension and treat them in a more physiological way. This would be the subject of the next Doodly. Hoping to see you in that one. Thank you.